Okay, hello. How you guys doing? Must be doing pretty good today, a little chatty. All right, we're gonna go ahead and get started. Last time we were covering the first part of how the mass balances can work out when it's a little bit complicated. We have growth, we have depth, we have substrate utilization, a lot going on, but using the tools that we've learned so far, we can navigate it. And today we're going to see when we recycle, we can get some different parameters and manage the system quite well. So we'll solve a couple problems, take a look at that, and I've also now posted the final formula sheet for you. Oops, let me get this over here. So there will be quite a few things here that you'll see that we've had before, and then several things that we have not talked about yet. A lot of this stuff. We will get there soon, and then this portion that we will wrap up talking about all of this stuff today. Some of this you've seen already. Remember, these were the specific mass balance derivations that we talked about. So only applicable for those scenarios. So we'll talk about that again today, but that's now posted for you. Just wanted to let you know. Okay, so last time we made this mess on our slide to answer part A for this this problem. Let me find my pen. Where did I put it? Okay. So last time we left off at this slide, and from here we went on to begin part B and C, or well, I guess we already did part B or have the answer enough. And so what I wanted to do today is pick up here, tell you about it. I went ahead and included my solutions from last time, so we'll just step through it. We kind of covered all the new parts of this problem, and so it's just algebra from here. So we'll just step through a prior set of solutions to answer part B and C. But just to remind you, what we're dealing with is this pond. We wanted to know first, the first part, what is the BOD? What is that substrate, S, concentration leaving, and how do we find that? So we ended up doing the counterintuitive thing, doing a mass balance on X, which because there was no X coming in, we had some variables cancel. That was quite convenient. So we ended up with our solution to solve for S by first doing a mass balance on X. A little bit backwards feeling, but that's the way it worked out. We solved that. We found this equation for S, and it turns out if we put the numbers in there, we'll see it's about 7 milligrams per liter remaining. From there, we would calculate B and then go on to C. And so last time we talked about the approach to C would be then to do a mass balance on S. Now that we have X, we can put now that we have S, we can put S in where we need it and then solve for X. So that's what we would do next. So just revisiting A, when we put in the numbers, we end up with 6.9 milligrams per liter of BOD per liter, and that's based on the parameters that we were given. To take the efficiency, we would take the initial S minus S divided by the initial S, multiply that by 100%. We'll get an answer to say that this pond is 93% efficient, or it removes 93% of the biodegradable organic matter. Okay, so that's just punching in the numbers. These are all numbers. If we look back at our equation, the Ks, the 1 plus theta Kd, we'd have to solve for theta, but you know how to do that. That's V over Q. And we'd have to take our parameters from over here. The table that was given, we were told to use default parameters, so there we go. So all of that, put in that equation that we derived, we should get our answer there. So that gives us A and B. and then we're on to part C, where we are doing this mass balance on S at steady state. So we're going to set up to track the changes of S in our solution. We have, since it's steady state, zero accumulation equals what's going in minus what's going out, plus that rate of substrate utilization within that volume. So we have QS naught minus QS plus this rate of substrate utilization. And again, the negative sign for, because we're consuming the substrate, that'll appear there in the, when we write out the actual rate equation. So with that, we will put in the pieces there and then solve for X. So we have 0 equals QS naught minus QS minus V, and now here we are putting in RSU. So RSU, we talked about last time, is negative RG over our yield coefficient. When we put in our RG is here. That's essentially our first order growth equation, mu x. Okay, so RG is mu x. When we correlate our substrate utilization to the growth rate, it's proportional to our yield. We're getting some amount of bacteria yield per some amount of substrate. And so we can track how much we're using based on the negative of how much is growing, also accounting for that yield. So that's all coming into here with this little bit of math. We talked about that last time. And we know that we define this K, this maximum specific substrate utilization coefficient, as the maximum specific growth rate coefficient divided by the yield coefficient. So all of that piecing together can get us a value for RSU that comes in right here, including that X. Okay, so all that to say, we substituted it in. Just negative RSU goes into right there. Okay, with that, now we have X showing up. We can simplify a bit, divide everything by Q. This becomes S naught minus S minus V over Q would be theta. And we end up with the equation here. So we have S naught minus S minus theta X divided by Y times mu, which is mu max S divided by Ks plus S. All right, with that, we need to solve for X. Takes a little bit more algebra. From this stage, and we should be able to rearrange and get our equation X equals Ks plus S times S naught minus S divided by theta Ks. Again, keep in mind the lowercase k and the uppercase s. This is different than the half velocity constant, which is an uppercase K with a subscript S. Sorry about that, but this is following the book here. All right, so with that in mind, we have an equation. This is the equation that I'm giving you on the formula sheet. And we now can solve for X. That becomes 43 milligrams of volatile suspended solids per liter as our answer when we put in all those numbers. All right, does that make sense? Okay, so mostly this was just a little more algebra, setting up another mass balance, and solving accordingly. Okay, so moving from there, I want to talk about what we do more often in practice. Sometimes we'll use some sort of a pond type of system for a small scale treatment operation, but many times we're doing this aerated system where we're going to collect the sludge, recycle it, keep a nice high concentration, of our bacteria, allowing us to perform better treatment, a more efficient treatment, faster treatment. So as we've talked about, this will look something like having a clarifier for our primary sedimentation. Then we get the effluent from that primary treatment. That's why we say primary effluent here. that's going to be the influent to our secondary process. Okay, that's what's coming in. That's going to meet whatever we're recycling, whatever sludge we're recycling. So now we might consider, and we will later in the class today, a mass balance on this little juncture to understand what's really entering our tank. Okay, because it will be a little different than what's coming out of the primary treatment and into our secondary treatment. And if we draw our control boundary out here, then we kind of have to keep in mind certain aspects of what's happening inside as needed, but the wider control boundary lets us simplify a few things, as we'll see. Because here we have one entrance and two exits, and the recycle is completely captured within it, and will simplify the math for us. Doing so will let us use our waste line, the WAS line, waste activated sludge line, as a way to control how much bacteria are in our system. And we'll elaborate on that. One thing I'll note here is that our Q coming in is going to be, should be obvious, but this should be equal to the Q as the secondary effluent going out of the clarifier plus however much flow rate we waste. So the W is sending it to waste. And this would essentially go to, this is like a small flow rate, sending it to sludge handling, essentially. Okay, so there's a lot we will get into with this. Bless you. But for the moment, just want to say here's our standard secondary treatment setup. So there's a few ratios, a few parameters that we need to know, a few equations that we'll take a look at. The first would be the food to mass ratio. So last time we talked about the importance of how much food does the microbe have, how close are they to maximally happy, right? That mu max goes into how much they grow, and how much they grow goes into how much food they'll take away, right? That treatment that we're looking for them to do. So we want to know the food to mass ratio, because that's really going to define what's going on in terms of how quickly they're eating. So this food to mass ratio, we're going to define this as F/m. This is how the book does it, and I'm going to warn you right now, we do not separate these as two different variables. The meaning is food versus mass, so food over mass, but in our class, for the math, for what we're doing, we're going to leave F/m as one variable, always. We're not going to separate this, aside from the fact that our definition here, in effect, separates it, but do not multiply m from both sides or anything like that, okay? Leave this as F/m. Sorry, but I'm just going to follow that protocol. Just keep this as one variable. This is convenient because from an operational standpoint, we can say this is the ratio of how much substrate, how much food per mass of bacteria that we have, and that ratio can tell us something about how we need to operate. So maybe we're targeting a specific F/m and operating accordingly, okay? And so this equation, practically speaking, is actually the food bacteria have per mass of bacteria over the course of a day. And so when we look at this equation, what we're going to do, the units here are going to be milligrams BOD per milligrams VSS. That's our mass of food per mass of bacteria per day. To get there, we can simply take the flow rate that's coming in times the amount of substrate that's coming in. So the flow rate times the concentration will give us a mass per time. Dividing this by the volume times the concentration of bacteria, which gives us mass of bacteria. So it's fairly straightforward. This is one of the equations I'm giving you. This is Q is the flow rate coming in times S naught, the amount of food coming in, divided by V, the volume of our aeration tank. and X, the amount of bacteria or the concentration of bacteria in our tank. One thing you'll note is we're only concerning ourselves with the volume of this tank despite having some volume here. We'll talk about it in a minute, but we're going to assume that's not useful for any reactions because we're not bubbling air through it. And realistically, stuff's not staying there for a long time. So we'll come back to that assumption. It turns out to be a pretty reasonable assumption. It's going to simplify things for us to keep the volume and our attention just on the reactor. Okay, so with that, we're keeping in mind that this mu that we tells us about these kinetics depends on the food, and so we really need a good food to mass ratio to keep our operation functioning like we want it. If, for example, we didn't notice it, but we had a whole bunch of dilution from some storm that brought in a lot of rainwater into our sewage system, infiltration and all that, well, suddenly we might not have enough food for the microbes, and they kind of get a little lazy on us. They don't grow very fast, and then as things change, if we didn't adapt for that and perhaps recycle maybe less microbes to keep the food to mass ratio similar, then suddenly in a few days when conditions change again, maybe our bacteria aren't growing fast enough and they're no longer eating as much food. And so we have more food going to waste, or more substrate, more waste discharged than we were supposed to. And our treatment is operating poorly. So we want a good range. And in general, we also, just kind of tangentially, we want a good food type. If bacteria are used to munching on the typical stuff that's flushed down a toilet, and suddenly we feed them a whole bunch of oil and grease from, I don't know, a restaurant grease or something, we might have the wrong bacteria to handle that. There probably are some bacteria that can do it, but if their food changes, suddenly, we might not get the good biological activity. They might not be adapted for it. In some cases, we might have sludge that starts floating. That becomes a very big problem for several reasons, because the primary task of this secondary clarifier is to make sure that the bacteria leaving out the top is close to zero. In fact, we'll assume it's zero normally. If we can do that, then all of the bacteria, we didn't want them discharged anyway, and the food that now is inside them, there's a lot of organic matter that these microbes have taken and built new cells on. Some of it they're converting to CO2, breathing, respiring, and all that. But some of it they're just gathering into microbial mass. So we don't want that microbial mass, all that organic matter, to discharge into the rivers and waterways. And we also really, really need to recycle bacteria cells so that we can keep the function of our aerated chamber working, to keep the food and mass ratio correct. So if microbes start floating and making like a scum layer and bubbling up and being filamentous and stuff, this does happen sometimes, and suddenly they're leaving, well, we no longer have the recycle, so our bacterial mass in our system drops quite a bit, and now we are not treating nearly as much as we should be. So we'd have to stop the system, but we can't stop the system because more wastewater is coming. We'd have to slow it way down to let the bacteria grow again. It makes everything a nightmare. If bacteria start making floating flocks and leaving through the clarifier, it is very bad news. So if anything disturbs the type of food or triggers some event where some unwanted bacteria starts growing, something that's not so good. We had that yogurt example from last time. If we got some other bacteria, not the probiotic yogurt stuff, if it was something nasty or wrong, we don't want it, right? If something, bad things happen. So that could also apply to the wastewater scale. So there's actually quite a bit of mathematical modeling that can go on to say, okay, which bacteria are growing, how fast are they growing, how does that depend on the food they're getting, in order to try to control and make sure we're getting consistent, no disruptions for our bacteria food. Okay, so that's all that to say this food to mass ratio is important, and that's kind of why. And we'll basically be controlling that or considering that as a way where we can relate how much substrate's coming in, given the flow rate, and how much X do we have, how much bacteria mass do we have in our system. Another item that we need to consider is not just the hydraulic retention time, which is obviously important, but we also need to know the cell retention time. How long does the bacteria stay in our chamber? So if we start recycling, we could have a situation where if we recycled all of the bacteria and they never go away, we're kind of like in an infinite holding pattern, which doesn't really make sense. We'd have too much accumulation. But we can adjust how long, on average, bacteria stay within our system by adjusting our recycle ratio. So that means we need to talk about cell retention time, or the hydraulic retention time, except not hydraulic, but solids retention time. So hydraulic retention time is not going to change if we change the recycle. And the reason for that is we have the same volume, and we're looking at the control boundary out here. The V over Q is going to be the V over the Q that is crossing this control boundary. You might say to yourself, well, aren't we speeding up the water that's going through here when we recycle? Well, yes, but that water is recycled. It's already been in there once. So it's maybe a little counterintuitive, but since it's just going back through it again, but we sped it up, it ends up canceling itself out, and ultimately the theta is not changing when we recycle, is the point. However, the solids do, because we have some separation with that clarifier. So we need some way to understand our solids retention time, and that brings us to this slide. So we want to know how long are the cells staying in there. How are we controlling that? Well, to get theta C, and this is for cells, not water here, we sometimes will call this SRT, solids retention time. It's not going to be equal to theta, so keep that in mind. We can derive this by saying, well, let's track how long the water is staying in there, but instead of just the water, we can multiply it by the amount of bacteria there, and that'll give us essentially our answer. So normally for theta, we would say this is V over Q. And in this case, because we have two Q's leaving, we could also describe this as theta equals V over QE plus QW, right? That would be the same thing. Now, if we take that and add the concentration of our bacteria in each spot, this would simply be theta equals Vx over the QE times XE plus QW times XW. Now, the trick is we have mentioned a minute ago that ideally XE should be 0. And that will be one of the assumptions. Right? So that means where we begin to have this theta C here, this portion goes to 0. And now we have Vx over XW QW. So this tells us how long the solids are staying in our system on average. And this also gives us a nice little window into why QW is important. QW is something we can change. You know, if we think about it, we have no control over Q. Aside from shutting down collection operations and telling people to flush their toilet somewhere else, usually not an option. You know, we have to have bigger design considerations before we do anything like that. So we can't really control Q. We have some control over X. We can't really control V once we've made the reactor, right? And the XW, that's going to be essentially however much concentration we pooled here, and that's kind of fixed just based on how much is leaving. So it is maybe impacted, but really our control lever is how much are we wasting compared to how much are we recycling. And so as soon as we take QW as a lever, that while it might affect XW, it also controls the whole system. So it turns out that QW is a really important control parameter. Okay, so that means if we want less mass in our system, we increase how much sludge we're discharging to waste. If we want to keep more mass in our system, mass of bacteria, we decrease the amount we're sending to sludge processing. So it's a very nice way to control our sludge retention time, meaning how much bacterial mass we have in the system. Okay, so that's quite important, and it's a nice relationship that we can establish in this system. Okay, I thought I had a slide where I was going to highlight these assumptions clearly, and I don't know if I misplaced it or what, but I'm just going to write them here just to be very clear. So our assumptions for this system is XE should be 0. Again, in case flotation happens, that's not good. Q is going to be QE plus QW. We also know that if we take a look, whatever concentration of bacteria that are leaving towards the waste is going to be the same as whatever bacteria we are recycling. So XW will be equal to XR, right? That's just, should be obvious when we see a split in the pipe does not change the concentration. The clarifier could change the concentration, but the split in the pipe cannot. A membrane might be able to change the concentration, but a split in the pipe cannot. Okay. So XR equals XW, XE equals 0. I think those are the primary ones. There's one more. We would also say the volume of the clarifier is effectively 0 because we're going to assume no biological activity in the clarifier. Fairly certain I had this all written out, spelled out on a slide, so I'm not sure where it went. But those are our primary assumptions. That lets us derive and use those equations we just talked about. And what you'll notice is now we have several equations that are handling things like S and X without going back and doing a mass balance every time. But they are coming from this mass balance approach where we draw a control volume and set up relationships. Now, maybe the mass balances come into play when we have to figure out what is a good food to mass ratio or what is a good cell retention time. But that gets way beyond the scope of our class. That's systems of differential equations and mathematical models to understand the proper bacterial growth and all that. So if we want to go there, people do go there, and there are well-developed systems based on the principles we've been learning. But for the moment, we're going to just take this look at how do we operate it? How do we design it? And take that approach. All right. So moving back forward, okay, maybe here's the assumptions that I kind of glossed over it. So here's that volume. Volume is only attending to the volume of the chamber. Okay, anyway. So here's a problem that I have given on exams before. So take note that this is something that I could use, or you could see something like it. And this is going to essentially discuss and give you practice with both last lecture and this lecture. And I'm just going to focus on today's lecture and show you where you could practice from last time. But I'll give you a couple minutes to take a look and see for yourself what sense you can make of it, and begin working on it. We will step through it, and I have multiple parts. We'll just start with A. I'll read it. You can definitely do A, and then I'll give you a couple minutes to think about B, C, and so on, and then we'll solve the pieces that I'll task you with a little more time and have you solve for the other pieces. Okay, so here we consider a wastewater treatment plant that is being renovated to include a return activated sludge line, or RAS. Assume the influent MLVSS, and by the way, that's one term I haven't mentioned yet. That is mixed liquor suspended solids. That just means, or mixed liquor volatile suspended solids. That's just our X, okay? And in this case, it says influent. So influent would be kind of a funny term, but mixed liquor, it's a sludgy mixture, essentially. Okay, so the influent MLVSS concentration is 0 without the recycle line. That should remind you from Tuesday's lecture. Then the following parameters are known about the reactor, which is functioning as a CSTR. So we have a flow rate, we have a volume, we have that half velocity constant, we have a maximum specific growth rate, a decay rate, a yield coefficient, substrate concentration coming in, that would be our S naught. And the new system is designed to have a solids retention time of 8 days. Okay, so the first task, even before we draw, might be good to go ahead and label each of these coefficients and things to make sure you are understanding what this problem is saying when it gives you all this lingo. Okay, so take a moment, see if you can do that, and then draw the schematic accordingly. I'll give you a couple minutes here and check in with you. All right, so hopefully tracking with this mostly. Before we add any recycle line, you could draw clarifiers. It might have them if it's unless it's a pond type of situation where you get some sedimentation by default. You're probably going to have some sort of primary treatment, and that's going to come in. So I don't mind too much if you didn't draw that. That would be fine. And likewise, you know, a pond type of system probably wouldn't have this clarifier. So I'm actually fine if you didn't draw this either. Oops, wrong one. You could maybe just leave it like that. But if it's more of like a concrete type structure, there's probably going to be some sedimentation. So maybe leave it, maybe don't. I'm not too concerned either way. The point is they're adding the recycle line. So the simplest answer to this one would look like this, but you would definitely need to have at least this portion for your second, right? You have to update it. You have to have something to separate your solids and to bring them back and recycle them. So that's kind of the difference between what we talked about Tuesday and what we talked about today. Now for the parameters, really this, you could just go back through the notes and look this up, but the half velocity constant, that's uppercase K subscript S. The maximum specific growth rate, that's mu max. The endogenous decay, that's our death rate for the microbes, KD. The yield coefficient is Y. The substrate concentration of the primary effluent, that's the stuff coming in, right? So in both cases, we have some effluent from a primary treatment coming into our activated sludge, in which case maybe it does make sense to draw a little primary treatment or just consider it as primary effluent. Okay, and then the solids retention time, we just talked about that a couple minutes ago. That should be theta C. Okay, make sense? Any issues? All right, so part B says, what is the final substrate concentration in the no recycle system before we add that return activated sludge line? So take a moment and reflect on what we talked about today and on Tuesday to decide on your approach. Right, so hopefully you're recognizing this. We need to take that mass balance approach we talked about on Tuesday. We derived a couple of equations. And in this case, this was the counterintuitive spot we're trying to solve for the substrate concentration. We have to actually start with the mass balance on X. And I'm just going to say practice on your own if you'd like to. Okay, so it's the same process we talked about Tuesday. That's the key part, is to recognize what you need to do, what you need to use, and the fact that our mass balance on X yielded us this equation. This was specific to a no recycle system where we had bacteria growth and death, of course, and substrate utilization, right? Specific to exactly this situation. It also means, it also called for the fact that there should be no bacteria in the influent, which was what we saw. Assume the influent concentration was 0, right? So that plus the no recycle gave us the ability to say we can use this equation, x naught equals 0. That allows us to use it. If any of those pieces were different, we can't use this equation, right? That's the caveat to me giving you this, because in general, I haven't been giving you the solved version of a mass balance because mass balances can show up differently if you change any one parameter or any one feature of the system. This one's complicated, and I just wanted to let you have this in case we cover this scenario. Okay, part C then, this parallels the problem we wrapped up at the beginning of today's class. What is the removal efficiency? And then part D, as you should be able to see, again, maintaining the no recycle system, what is the MLVSS? Should be the same deal. We're doing a mass balance. We did a mass balance on S, now we do it on X to get, excuse me, I said that backwards, right? Yeah. Mass balance on S to get X. Okay, and the efficiency, of course, would be a simple efficiency calculation. Okay, so I'm leaving all of this to the realm of practice on your own, and if you didn't recognize this is what you needed to do, reflect on that and work on understanding what the problem is saying and where it's leading you, okay? And feel free to ask me any questions on that. So, all the way down to part E then, we have if the sludge produced has a concentration of 12,500 milligrams per liter of VSS, which is now recycled via the new recycle line at a flow rate of 150 cubic meters per day. What is the resulting influent MLVSS? And I put influent in quotes. That's the stuff that's actually coming into the reactor, entering the aeration tank. And I give you a hint, refer to your drawing, so maybe draw it up again, and do not overthink the problem. Okay? So I'm going to let you overthink it for a few minutes and let you solve this. You should be able to do it, and it should be perhaps simpler than you realize. So overthink away. I'm going to give you maybe 10 minutes. Or don't overthink it. That's good too. Feel free to work together. Feel free to ask me questions. Start by drawing it. All right, how many of you got stuck overthinking it? It's not shameful if you did. Okay, how many of you feel like you got it? Okay, some of you. Still in progress? Some others, maybe? Okay, I'm going to give you a couple more minutes, but I'm going to give you one more hint here. When I say don't overthink it, you could have solved this problem without any knowledge of the class. Or maybe the first time we ever talked about any mass balances. The key is to focus in on exactly what the question is asking, and you realize all you have to do is look at what's happening here and find whatever this x in is, recognizing you have a q plus qr right here. So you're doing a mass balance on two pipes coming together to figure out the x coming in. And you kind of have all the other information. So how many of you were overthinking it? Okay. All right. So that's the tricky thing about learning a bunch of stuff. Sometimes it's difficult to take a step back. All right, so take 2 more minutes, see if you get that. All right. How you feeling? Okay, some good, some not so good. All right. I'll walk you through what I just did. You can kind of check yourself. I also went over to Excel real quick to do it. When we take a look at this juncture, well, first of all, we have to draw our system, right? So we had to get part A correct in drawing out what we had talked about earlier today, that we have recycle coming from some clarifier, joining the stream that's coming into the reactor as a way to give us more bacteria coming in. Okay, so when I defined this influent, what I was really referring to is what's happening right here. What's actually going into that reactor? That's what I was referencing with this influent. Okay? So that's my target, is to understand that X into the reactor, which is different than what's coming out of the clarifier before. Different than our primary effluent, which had 0 bacteria. That was the X naught equals 0, but here we want to know what's X in, right? That's the question. So understanding that question is key, and recognizing that it's going to change because we're recycling, right? That's giving us more bacteria coming in. So then we draw a control boundary around that juncture. So a lot of times we're doing this control boundary around the entire system, but for this problem, we can recognize what's coming into this juncture in the pipes is what's going out of the juncture in the pipes, okay? There's not really much time or volume for any reaction. So we're going to neglect all that and say the mass balance is what's going in is what's equal to what's going out, right? Almost like we're mixing 2 bottles of water. What's coming in is going to give us the concentration of what's the finished product, or 2 streams coming together, right? And that's why I was saying what we did in probably the first day of class, or first day talking about mass balances, 2 streams meeting is all we really need to do. And even that is intuitive enough that we could probably figure it out. But it's nice to put it in this nice fancy mass balance term, so we can do that. Say what's coming in is the QX naught, that's 0, plus the QR that we're recycling times XR that we're recycling. So those 2 are our inputs. One is diluting it, the other is carrying microbes, and that will be equal to what's heading into the reactor. So we can solve for this X influent in that flow rate, which is going to be the combination of the recycled flow rate and the total flow rate that was coming in from our primary clarifier. So given that, we can rearrange, solve for X in. That'll be XR QR divided by the 2 flows together, QR plus Q. Solving that, we can put in our numbers. We were given the numbers for this. Should come out to be 1,850 milligrams VSS per liter, approximately. Now, we did have to account for the difference in time units for the flow rates, 150 cubic meters per day. For the recycle line, it's a lot smaller than our 0.01 cubic meters per second of our big flow. You could change that either way. You could have converted the Q instead of the QR, whatever you like. I just happened to write it this way. You'll get the same answer. So the Q units drop out once we get them consistent, and then we're left with that X. And we can also double check ourselves. It should be greater than 0, and it should be less than the recycle, right? If we got some answer that was more than what we were recycling, we did something wrong. So we can check 1850 is decidedly smaller than the 12,500 that were in our recycle line, and certainly larger than 0. So feels pretty good. We have some bacteria coming in. Our recycle has been a success, and we are essentially priming our reactor with some bacteria. All right, does that make sense now? Am I good? Okay, so when I said, oh, don't overthink it, we didn't really need anything we learned yet today, right? Aside from just setting it up and understanding what this reactor is looking like and why it's functioning that way. Okay, so now let's get to something maybe we did learn today. So part F, in a new system with the recycle line, the resulting food to mass ratio is 0.58 milligrams BOD per milligram VSS per day. The question is, what is a new MLVSS concentration in milligrams per liter? Okay, and just as a reminder, we have an equation for food to mass ratio given there. So take a minute and solve for that. Okay, so I put this one up here already for you. Just did the math in Excel. So the question is asking for what is X in the reactor. Right, of course, it would be good to go back and refer to the drawing if you needed to, but the new MLVSS concentration, milligrams per liter VSS, that should be asking us what is X. And by the way, what we've done here is we've just defined some food to mass ratio and discussed it from there. So this is, if we think about the previous question, well, maybe if we have more than that coming in, maybe this value should be larger, but we've let the system come to some equilibrium where this is the food to mass ratio. And so that's how we're defining it. It's kind of a little disconnected from the one prior. Question? So the food to mass ratio is a very good question about why not add QR here. The food to mass ratio is talking about the amount of food that the reactor is receiving per day and comparing that to how much mass is in the reactor, mass of bacteria is in the reactor per day. So the way we define how much mass of food is coming in per day is the Q that's carrying the S naught. So if we were to go back to our drawing a minute ago, we are looking at this term, the Q coming into the entire system times the S naught coming into the entire system. So that's why we would not consider the Q plus QR. And again, that's kind of handy that we define the control volume beyond that for most of our work, so that we can look at it at kind of a bigger picture. Okay, so given these parameters, and given that we have all the pieces, we can see earlier, probably it would have made more sense for me to put the Q into per day instead of putting the QR into per second. So I went ahead and put the Q from 0.01 cubic meters per second into per day. That's 864 per day, cubic meters per day. So with that, we can use our food to mass ratio, which is in days. You could have converted that to seconds. That would be fine too. But this is what I did. We've got S naught, we've got the volume given. We now have our Q in per day units, and we're given some food to mass ratio, so all we'd have to do is rearrange that. And here again, just take F/M as one variable. Move it around as one variable. Don't play with it. You'll just confuse yourself if you do something different, right? So just move that as one variable, and we can swap it with X in our equation, and we can solve for X. That should give us 595.9 milligrams VSS per liter. Okay, good on that? All right, so almost the last piece here. So the question goes on to say, what is the flow rate of the waste sludge line? So what is QW? And we can assume some value. If you missed the previous part, I'm saying assume a value of 400 milligrams VSS per liter if the other one wasn't reasonable, just to kind of give you a scope. So you could solve it one way or the other. We are short on time, so I'm going to go ahead and give you this. I'll give you 1 minute to work on it, and then I'll solve that with you. All right, so for this problem, we're using our theta c equation because at this point we need to know something about QW, and we have every other piece of information, or if we didn't, we were given a piece to use, that x value. So we can check this for either x value, the one we solved, or the one that the problem gave us. And really, all we need to do is rearrange our theta c equation to solve for QW. Okay, and swap those two. The only other piece that might be complicated is what is XW? Well, earlier in the problem, we defined an XR. We were given that, so we could just make use of that same one, 12,500 milligrams VSS. And so if we do that, then we can rearrange, put in our numbers, and we should get values of either 2.2 cubic meters per day or 3.28 cubic meters per day. So it's a pretty small amount of sludge that we're wasting compared to how much water we are treating, essentially. Okay, does that make sense? All right, last one. It'll only take a moment of thought. What is the hydraulic retention time of the activated sludge basin before and after the recycle line was added? You can solve it in 1 minute. Go. All right, did you get it? It's the same thing, right? We talked about this, right? So you can just take V over Q. It's the same thing for both. Should be 0.64 days for both. Okay, there you have it. There's pieces there that you can practice. You can look back through. And next time we're going to talk about what happens when you discharge the waste. What is this BOD? How do we calculate it? How do we deal with it in nature? So have a good weekend. We'll see you Tuesday.